is that a directive or?
Yeah, Zach, do you want to start sharing your screen and then we're all ready to go? Okay, hello everybody, and thanks for joining us for today's Earth-to-Earth seminar. Earth-to-Earth is organised by a governing board with representation from a range of UK universities, from Nature Geoscience and from the British Geological Survey. Please visit our website, earth2earthseminar.com, for information about the series, about future seminars, or to nominate a speaker to speak in the series next year. You can also follow us on Twitter, and we now have a mailing list you can subscribe to, and again, details for that are available on the website. It's our mission to engage the UK geosciences community with inspiring science from internationally leading researchers. And we will do this while promoting inclusivity and diversity and supporting the advancement of early career researchers and highlighting geoscientists' contribution and potential contributions to addressing global environmental challenges. Today's seminar will be recorded and will be available on our YouTube channel after the seminar is finished with closed captioning. You can also find recorded versions of previous seminars on the YouTube channel. During seminars, we ask that you follow our code of conduct, which is available on the webpage, again, earth2earthseminars.com. For questions, please use the Q&A function, which is available at the bottom of the Zoom feed. And we will also be monitoring the comments section on the YouTube stream for any questions that are posted there. We should have 10 minutes at the end of the seminar for me to relay questions to the speaker and for him to answer them. Now, it's my pleasure to introduce today's speaker, and we're fortunate to have Zachary Ross joining us today from the California Institute of Technology, where he's an assistant professor. Zach did his PhD at USC in Los Angeles before moving to Caltech, first as a postdoc, and then from last year on an assistant professorship. Last year, he also won the Early Career Section Award from the Seismology section of the American Geophysical Union. So we're very grateful to have Zach talking to us today. Zach, go ahead, begin whenever you're ready.
Okay, so thank you for the invitation to be here. This is a very different audience for me, so it's good to kind of be able to reach out to a new crowd. So today, I'm going to talk to you about I think just one of the most incredible earthquake storms that we've seen in Southern California going back decades, and what we've been able to see from that, tracking it kind of in slow motion, and what we've been able to learn about that and how that might be related to underlying properties of fault structure as well. So, okay, so to get started, whoops. So I just want to give a bit of overview on different types of earthquake sequences, because I'm going to be using this terminology here. So there's typically today, I think, viewed as two main types of earthquake sequences. And the first of these is what most people will be thinking about as a typical kind of main shock aftershock sequence, which is something like this, where if you look at magnitude versus time, you have a big event of some kind. So here, magnitude 5, this is from 2014. In Los Angeles, the La Habra earthquake sequence. This might be preceded by some foreshocks and then followed by aftershocks, which decay with time in terms of the rate of them. And this follows a Maury's law, 1/T. And if you look at something like this, I think today it's fair to say that that we generally understand the bulk behavior here, this kind of decay with time, and we think that that's related to some form of earthquake stress transfer. And that, predominantly is related to static stress changes imparted by a main shock, or it could also be related to potentially dynamic stress changes from seismic waves. But there's another type of earthquake sequence that's fairly common among natural seismicity, and that's the earthquake swarm. And this is a much more complex process that I don't think we understand all that well. And so swarms, here's an example of one like this. So this is from almost 20 years ago now. This is in southeastern Germany. And you can see here, so in comparison with the previous slide, the rates don't just simply decay with time. They're modulated potentially. It's very complicated. And so swarms are associated with areas often that have some kind of elevated heat flow, rifting behavior, hydrothermalism, and so forth. Although it's not required that these are the case, but that's commonly where we see them. Now, each swarm, one of the things that's special about them is that they seem to have some kind of unique evolutionary pattern in space and time. And that really stands out compared with a lot of these main shock aftershock sequences. And during a swarm, the behavior is, as you can see up here, it's often highly non-stationary. And so this, in terms of earthquake forecasting, it makes it very difficult to predict what's going to happen next. And simply because the rates can just shut off abruptly, they can turn on very quickly. And so they generally have a lack of this kind of a Mori decay property that main shock aftershock sequences have. But there's also several other characteristics that I think are fairly common to see among swarms. There's about 4 or 5 of them, and I'll kind of try to highlight these here. One of them is that the largest event will often occur quite long after the swarm initiates. And so you can see that here. So for example, the largest is about a 3.2 or so, and that's about 70 days into this sequence. And if the whole thing is only 120 days long, that means that it's later into the sequence than it is closer to the start, which is very different from these main shock aftershock sequences. And often what we will also see with swarms is that there's no clear main shock event. And so here, for example, you can see that there's many other events that are above magnitude 3. Typically with main shock sequences, the largest event is 1 to 2 magnitude units larger than the next biggest event in the sequence. And this is not the case commonly with swarms. Now, swarms often will last days to months. They could be slightly longer. Occasionally, they could be 6 months or more, but those would be generally quite rare. And they will often exhibit some kind of spatial migration. If you were to just plot up the hypocenters, you could see some kind of pattern that's moving, it's diffusing, something like that. And so together, when you take all of these properties that I've discussed here, together with various other lines of evidence, today we believe that earthquake swarms are driven by external processes, and the leading candidates of these are fluids and aseismic slip. And so this is very different from main shock aftershock sequences where we believe that they're being driven by earthquake stress transfer. So this is some kind of external process that's driving this. Although it's not necessarily the only process driving this. So it could be, a mixture of static stress changes as well as one of these other driving processes. So if you put these side by side, you can see really how much complexity there is in a swarm. And so this is something that I think we understand, but I can't look at this plot here and say, I really understand what all these bursts are and why they just abruptly shut down like that. And so most of the complexity that we see here remains unexplained to this day. And so the hypothesis that's going to be explored here in this work today is whether some part of this complexity could reflect limitations in our knowledge of the structural and permeability architecture of fault zones. Because if we believe that swarms are driven by things like fluid migration in the Earth, then properties like permeability architecture is probably going to be very important. So with that, it leads to the question of what we really know about these properties of fault zones. So I'm going to start off by talking about the structural architecture and then move into the permeability structure. So structurally speaking, I think today this is kind of the standard view for a fault zone in terms of structural properties. So fault zones are hierarchical volumetric systems where you have something like a principal slip surface that's very localized in the order of centimeter scale. And that's going to be contained within a fault core, which contains things like wear products, gouges, cataclasites, stuff like that. That's on the order of meter scale. And then surrounding this, we will typically have what I'll just call here our inner damage zones. These are on the order of several hundred meters wide. And so this is highly fractured rock where the decay or the fracture density will decay exponentially with distance from the fault core. Now, beyond that, we often see, especially from seismology, evidence for distributed damage zones that can be kilometer scale, 1 to 10 or so. But it's important to note that, it's not just a single fault or single surface, that these systems have many smaller faults and cracks that are embedded within them at many different scales. And so these are truly hierarchical systems. Now, in terms of the permeability structure of fault zones, so here's a cartoon with a fault zone in it. And if you were to scan across this, like they've done in this diagram here, typically the permeability structure of fault zones is discussed, especially by hydrologists, in terms of fault core and fault in the damage zone and the permeability properties of those. So if you were to move across this fault zone here, this is basically characterizing the fracture density of that and the permeability as you move across it. So here, for example, as you go through the damage zone, the permeability starts to go up and then it drops, in this case here, as you go across the core, and then goes back up again and then decays related to the fracture density. Or if you have multiple strands like you do here, you just kind of repeat this pattern several different times. And so this has kind of led to at least some kind of models that general models that have been compiled where you can talk about kind of barrier conduit systems like here, where if you look at basically the percentage of the fault core in terms of low permeability materials, and you compare this with how much of the fault zone is taken up by essentially the core or the damage zone width as described here, this can lead to various scenarios that are described here in terms of either localized conduits, or you could get a localized barrier to flow, or you could have something like this that's more distributed with a conduit or some kind of barrier system within it. So I think this is a fairly good summary of where we are at today in terms of understanding flow within fault zones at a very general level. It's also, I think, important to note that models for fault permeability are often viewed as being quite strongly anisotropic. So here, for example, they have the permeability ellipses to show how that might behave in different parts of the fault zone. And so here you can see that they're elongated within the damage zone in the strike parallel direction, whereas out here, for example, that it's symmetric. And this is important not just for seismologists or earthquake scientists, but also for hydrologists, where you often need to simulate flow in a region that has faults within it. And so here, for example, if you have aquifers at different depths and you have a fault that is anisotropic, that can allow for these aquifers to be connected just by having this anisotropy. So this is of broader importance than just the earthquake science itself. Being able to understand the permeability structure. So, so how do we get the information from these models? I think it's probably no surprise to most of you that the information from this primarily comes from measurements made at or near the surface. And so, this is looking at outcrops, taking samples, putting in flow meters, things like that. So, it's dominated by near surface measurements. Occasionally, we can augment this with samples from deep drilling projects. So, for example, this is the JFAS project from after the Tohoku earthquake in 2011. Sorry, this is still a little too early for me. But if you drill into the fault like they've done here, they can take samples of the megathrust material and bring it back to a lab and process it, look at the fault structure, like friction properties, things like that. And so this provides very valuable measurements, but I think it's important to point out that it's highly sparse. And so you measure this at a handful of points and you're kind of left with trying to generalize these measurements to, a continuous surface of some kind, which is very challenging, obviously. And so because of all this stuff, the fact that most of this information comes from near surface measurements, I think it's important to note that these models for what I'll call general fault architecture. And here I'm not talking about a single fault, which we know is three-dimensional, and often we can study a single fault in great detail and see the 3D variations. But the models for general architecture are effectively two-dimensional in the sense that we are left to kind of generalize these laterally heterogeneous models to 3 dimensions by basically assuming that most of this stuff varies smoothly with depth. And I think if I just go back here, for example, you can see that in this cartoon, pretty much all of the variability here is treated as lateral variability. It's really all talked about in terms of the core and the damage zone and how you move across this in a fault normal sense. And so, but we know that this is really not the case. There's been many studies over the years looking at individual fault zones, and we see that they are highly three-dimensional. And this has been especially so in the last decade, as better techniques from seismology especially have started to come out. And some examples of those are here. So this is a high-resolution tomography study done in Southern California on top of one of the major fault zones, the San Jacinto fault zone. And so these columns are VP, VS, and the VP VS ratio. And so these are at depths of 2, 5, and 8 kilometers. And so even with tons of smoothing that comes from a tomography study like this, we can see substantial variations as a function of depth within this fault zone, especially when you look at the ratio. They change on the order of kilometer scale with lots and lots of smoothing. And of course, if we could resolve the finer details of this at 100-meter scale, we would probably see much more significant variations. So it's not so surprising, I think, to expect that faults are probably very heterogeneous in 3D. Here's an example of this from the Ridgecrest earthquake sequence that we had last year. So this is from seismicity, looking at down to about 10 kilometers. And so these are all just hypocenters. And if you look at this cross section here, going from A to A prime here, from the seismicity, what we're able to resolve is on the order of about 20 small faults that are a few kilometers long, that will start and terminate fairly abruptly. And this is kind of all surrounding the largest structure here, which is on tens of kilometers scale. So we have this collection of many different faults. And I think, for a very immature environment like this, it's fair to say that probably most of these tiny faults don't extend all the way through the crust, through the seismogenic zone. It's immature. They haven't localized yet. And so therefore, you're left with a fault network that, if you think about this in terms of the permeability structure, these are not necessarily going to be continuous. Maybe there's distributed damage connecting some of these, but flow within this fault zone is going to be very heterogeneous. It's not just a simple surface that's independent of depth. And I think we have to kind of consider these properties a lot more, because if we want to understand the behavior of swarms, well, this is probably going to be quite relevant. So to go back to this diagram, just as I've mentioned before, we would like to figure out what all this complexity is here, why it's able to kind of start and stop very abruptly. It's not just a simple decay like Mori's law with time. And so if we think that maybe some of this complexity comes from very heterogeneous properties of fault zones, well, we need to start thinking about how those fault properties can affect seismicity patterns. And so if you want to talk about, driving processes like fluids, well, there's been models that have been proposed over the years to try to discuss how seismicity can be driven by fluids. And so this is one that's called the fault valving model. And so it's discussing basically injection-driven seismicity, but in natural earthquake sequences. And so the idea is that, maybe there's some kind of reservoir somewhere in the crust that's sealed off, and pressure within that reservoir is building up. Eventually, it reaches some critical threshold, and now all of a sudden fluid starts to flow, and it enters a fault zone that is capable of producing seismicity. And so you start producing events as this fluid is diffusing outward and through this fault system. And ultimately, it leads to some kind of sealing behavior, and this kind of starts to decrease and then repeat. And so this would, under this model, then you would expect that there is some kind of cyclic behavior where this fluid pressure just keeps building back up and releasing in the form of earthquake swarms. So this is important. I'm going to come back to this a bit later. So, okay, so with that, this kind of leads to the main portion of my talk in terms of the results. So, as I mentioned before, this swarm that we're going to look at here is really one of the most incredible sequences that I think we've seen in Southern California, going back many decades. And so, just to give you first a brief overview of the region. So, so this is a map of most of California here. So we're looking at this area, which is the very southern part of the plate boundary. So here, this is the part of the plate boundary where you have three kind of subparallel main fault systems. So San Andreas is here, San Jacinto is here, and then the Elsinore is right here. And so the sequence that we're talking about is this tiny little red box, if you can even see it on your screen here, which produced this sequence that we call the Cahuilla swarm. And so this is an area, basically the rock type here. This is the peninsular ranges, so it's crystalline rocks. The area has basically average heat flow. It's not known for hydrothermalism. It's not considered to be a classic swarm region, like the Salton Trough is, for example, which is just down right over here. So this is actually not even an area that people really even knew had swarms in it. So this in particular then stands out in that regard. And so this swarm started in 2016 and lasted for nearly 4 years, basically up until several months ago. This thing was still ongoing. And so this is therefore among the longest swarms that we've ever observed in California, going back about 40 years or more. And during that time period, it produced something like 15% of all the earthquakes in the Southern California seismic that were cataloged, just coming out of this tiny little box right here. So it's quite active, or was quite active. And this area also has a history of this kind of behavior. So back in the 1980s, there were two other swarms that were for several years, and they were also quite active, but it was basically quiet since about 1983. So this here shows the cumulative number of events versus time, and we kind of view this as being three different parts. So 1, 2, and 3 here. So it started off very slow to the point where we didn't even know that there was a swarm ongoing until basically around 2018, because the rate of events was so low. And actually, we first found out about this sequence because we received an email from a person that was living in the area that was right on top of it and was feeling these events and was starting to wonder what was going on. And so because of this, at that point, it basically was indistinguishable from background seismicity, because especially if you look here, kind of at the San Jacinto fault zone, this is basically very close to the most active fault zone in Southern California. So it didn't really stand out initially as being anything unusual, but it turns out that this has been basically among the biggest swarms that we've had. So if you remember what I said about before, that swarms often have the largest event substantially into the sequence, that's true for this one as well, where the largest event is a magnitude 4.4 that happened almost 3 years into the sequence. So I think that really kind of highlights the difference between a main shock sequence and a swarm. And you can see that after this occurred, it really changes the character of this. So it kicks off and the rate changes and it stays elevated like that for some time, and then eventually decays and starts to basically flatten out. And today, it's now basically over, with just a few events occurring every few days. So, excuse me. So that kind of gives you an overview of the sequence. Now, so many of you might know that one of the things I've been doing over the last few years is working on kind of new algorithms for improved capabilities for earthquake monitoring. And these have focused in particular on the use of artificial intelligence, deep learning algorithms, to do better than we ever could before in terms of automated processing of large seismic data sets. And so in 2018, when we had started developing these algorithms, we were fairly close to getting this stuff up and working. And so I mentioned before that we figured out that this swarm was kind of ongoing around that time. And this served, I thought this would be a great opportunity to kind of turn this new technology loose on this data set and see what we could learn about it. So I'm just going to give a brief overview of the algorithms that we developed and how we use them. So the first of these is basically an algorithm for single station earthquake detection. And the idea is that we have a machine learning model, a deep neural network. And in this case, it's a convolutional neural network that is designed to take a very large amount of human labeled seismic data. So in this case, it's seismic waves like this, the times of their onsets, and so forth. And we take a data set of millions of earthquakes, or millions of seismograms, I should say, and we basically train this model to learn from and generalize the decision-making process that a human seismic analyst can do to scan the data just like this and essentially output streams of probabilities of different types of seismic waves present in the data at any time. And so we can run this then on continuous data. And so in our case, it's going to be all of the single station data that we have, and collect a bunch of triggers by setting a simple threshold. So every time you exceed some threshold here, maybe it's 0.5, you just log the time of that type of phase pick. And you then repeat this for all of the different stations in your network for all of the data that you want to process. And so then what we have to do is basically connect all this information between all the different sensors. So because the algorithm before is single station based, we're stuck trying to link together stuff that should originate from a common source. And so this problem is referred to as the phase association problem. So here, if you basically have a wave field of triggers, so this is latitude versus time in a normalized sense for latitude. And so this is basically just a cartoon. So if every one of these is basically a tentative phase pick somewhere within the network, you can see that here we have this kind of coherent behavior where if red is for P waves and blue is for S waves, you can see this move out pattern within the network here. And so the problem statement is to basically group together all of these triggers that have a move out pattern and say that these all originate from a common source. They back project to a coherent origin, and say that that is an earthquake, and say all this other stuff here, this kind of incoherent stuff, that's unrelated, and those are basically false triggers. And so we have an algorithm that is designed to duplicate this decision-making process. It takes in a whole sequence of tentative phase picks like this, and what it ultimately produces is clusters just like this, where each cluster can then be taken and inverted for a formal hypocenter somewhere within the seismic network. And I'm not going to go into the details of how this works exactly, but we've been running this on tens of terabytes of seismic data at this point, and these algorithms are quite robust. And if you're interested in learning more, I encourage you to check out our papers. There's a whole bunch of them that have been published at this point. So what I really want to focus here on today is taking this technology, applying it to this data set, and really seeing what we can learn about the Earth. So here, to go back to our map of the region, so these are all of the seismic sensors that we're working with. So this is basically everything within about 50 kilometers, all the blue triangles here. And so when we run all this stuff end to end, so starting just from the raw waveform data, no prior seismicity catalog whatsoever, we end up with this, so 23,000 earthquake locations. So these are the original probabilistic absolute locations here. And so you can see from this scale that we're already talking about something that's fairly localized. So just from these alone, you're looking at something that's on the order of 3 kilometers or so. But we can do better than this. We can relocate this data set by using waveform cross correlation, forming pairs of all events within some radius, and measuring precise differential times, inverting this for relocated seismicity. And in this case, we use the GROW-CLUST algorithm, which is a cluster-based double difference algorithm for relocation. And so when we do that, that forms the seismicity data that's going to be the basis for this investigation. And so I want to begin this by first walking through what we can see about the geometry of this fault zone before I move on to talking about the spatial temporal properties of this sequence. And so here is a map of the final relocated seismicity This is colored by depth here. So we're going from 5 to 9 kilometers. And you can see initially very clearly that there is a clear color cycling from white to black, all the way through yellow and red and so forth, which tells us that this is getting deeper as you go towards the northeast here. So the fault structure is dipping. And indeed, if we take cross sections of this, so here x prime and y prime, you have these two cross sections as you see right over here. And so this is steeply dipping, but there are actually very interesting variations in the geometry of this fault zone. So here, this is fairly straight or fairly planar, I should say. But in this one, which is, only it's less than a kilometer away, we can actually see multiple reversals in the dip direction as a function of depth. So it kind of is near vertical here. It starts to dip towards the western side and then reverses and goes back towards the northeast. And there's kind of this curvature associated with this. And so there's this clear transition from this to this on fairly short length scales. Now, if you're looking at the seismicity, I think one of the things you can see is that there seems to be kind of these channel-like structures that extend almost for most of the distance along strike here. There's several of them. So this is one here. Another one is right here. And there's a third one here. And finally, another one at the base. And those coincide with these kind of high density structures within this surface. And so you can see here that there's kind of this band, and then there's a gap of seismicity here, and then a band, another gap, and there's another gap here, and so forth. And the same thing with this here. And so these gaps are on the order of several hundred meters wide, which is larger than the vertical resolution of our seismicity, which is on the order of about 80 to 90 meters here. So these are considered to be well resolved, and those gaps are considered to be genuine and not artifacts of the detection process. Now, I also want to mention that the fault zone here is very localized on the order of tens of meters, so maybe 50 meters at most, which again is comparable to the location uncertainty here laterally, which we estimate to be about 40 meters. So we can't even say if all of these would localize to a single surface with basically no width at all. That's all within the resolution limits. And so then we can take all of the events here. We can aggregate the depth across this entire region, which is not necessarily the best for something that's not kind of perfectly horizontal, but you can see that there are peaks and troughs here. Sorry, let me get my mouse. There's a peak followed by a trough, followed by a peak, another trough, and so forth. And this just keeps repeating. And if you've ever looked at depth histograms of seismicity, you might typically see kind of one or two big peaks, but not this kind of multimodal behavior like we see here, which is associated with these peaks and low density bands of seismicity that you see here. So hopefully this gives you a sense of what the geometry of this fault system looks like. Now I want to talk about the spatial temporal properties. And so the first is that, so this is, all these events are the same plot, except they're now colored by time elapsed. So starting from the earliest event of the sequence, all the way to the very end of the sequence, this is basically 4 years in. And this is a cross section of the seismicity here, going from Z to Z prime right here. And so if you look carefully here, you can see that this bullseye thing here, colored red, is where this swarm initiates. We can localize the onset of this back to a region that is basically on the order of several hundred meters wide. And so that, again, is considered to be very well resolved. You can then see that from this point, this swarm front is expanding away from that in basically some kind of radial diffusion-like pattern. So it goes from dark red to orange to yellow. And so it is moving very slowly away from this point with time. And eventually it hits this part here and it just kind of abruptly stops. So you see it goes from green to basically nothing. Whereas over time, it starts to continue, but it's moving slowly up dip. So it starts to approach blue colors here, and then darker blue all the way up here. And so there's some kind of barrier to continuing this migration laterally at the base of this. You'll also notice that it never really goes deeper. So it pretty much either goes laterally or up dip. It doesn't extend ever downwards at any point really during that 4-year period. And so I'll kind of just summarize right now what I think this is, and then kind of go over the various lines of evidence for this. So we think that this is associated with some kind of natural fluid injection process into this fault zone from some kind of deeper reservoir that was connected to this, but initially sealed off. And the fluid is therefore diffusing within that very narrow fault zone surface slowly over several years' time. And so let me walk through kind of the lines of evidence for this because it's all inferred from the seismicity directly. So if you recall before, I talked about these different channel-like structures. You can see that here, for example. So there's this high density band of seismicity followed by this kind of low density band of seismicity. You can also see another one of those here, followed by another low density band and another high density band here. So these channel-like structures are actually aligned in this horizontal sense. And I'll get to this in a second, but they turn out to be aligned with faster migration rates within this fault zone. And so all these arrows are pointing to these high density seismicity bands. But if you see here, as this swarm starts to move up dip, it gets to this point here that I've labeled as a barrier. And if you look very carefully, it goes from basically a light blue to a dark blue on the other side of this barrier, rather than going through this kind of intermediate blue here. And if you look closely at our color scale here, that's about a year's time elapsed between when it goes from this light blue to this dark blue here. So it actually stops moving up dip at this point and actually has to circumvent this down here and then moves across in a lateral sense. And to give you a clearer visual of that, I've divided this into the seismicity before it hits that barrier and then after that barrier. And so you can see here that it kind of stops right here and has to start moving up dip through this kind of narrow aperture within the fault surface. And again, remember the fault zone is only on the order of tens of meters wide. So it's moving through this kind of slit within the fault zone up dip like this. And then it kind of moves across laterally from there rather than just simply migrating up from here. So there's some kind of barriers to migration within here. And again, we think that this seems to relate to variations in permeability structure within the fault zone. And so I want to point out that all of this kind of banding, this channeling of the seismicity going from high density to low density and again to high density and so forth, this is very similar to what has been seen in, for example, simulations of flow within fault zones. So if you take a fault zone and you have kind of host rock that's assigned or damage zone related flow patterns or permeability, and then you add in a bunch of cracks like this and you assign them, permeability for a core, well, you end up with channeling of flow. So high values of flow here are dark and low values are light colored. And so this kind of channeling of flow just happens automatically from having heterogeneous permeability structure within a fault zone. And so that might be related to what we're seeing here. And so we can try to analyze this a bit more quantitatively. We can take this point as the origin and measure the radial distance of each event from that point. And that's shown here. So it's distance versus time in days, but it is projected into a long strike and a long dip component. So red is a long dip and black is a long strike. And so you can see that this swarm expands from something that's on the order of about 100 meters wide to something 30 times the size in about 4 years' time. So this is growing very, very slowly. It's on the order of about 5 meters per day or less. So you can see this clear expansion front like this. And it turns out that the along strike component starts to become faster than the along dip component starting about 2 years in. And that coincides with the time at which this front starts to hit these prominent channel-like structures down here within this fault zone. And so maybe that implies that this kind of channeling and flow is, anisotropic preferentially in that direction from the permeability structure. And then another thing I want to point out here is that here you see the effect of the magnitude 4.4. So this is the largest event of the sequence. So that comes in almost 3 years in. And immediately you can see that this changes the character of this dramatically. So it goes from having very kind of scattered hypocenters here to this very prominent vertical streaking here. And so that, I think, is related to the fact that here you've introduced a big static stress kick to the system. And here, this is probably being driven primarily by this fluid pressure diffusion. And so here, this is kind of illustrating the effects of what happens where you now add this one big event and you've pressurized this whole thing. And so you add in all this clustering, this earthquake clustering. And the last thing I'll add here is that you can see this kind of low density seismicity here near the source while it continues to propagate away from that. That might tell us actually that the injection stopped starting around this point in time and the fluid continued to diffuse away from there. But maybe this starts back up again when you have this big event here and starts to trigger events back near the source region again. So we can take this and try to estimate something about the fault zone permeability structure from this. If you assume a very simplified point process diffusion model with a homogeneous permeability, you would assume that that form would then be some kind of square root of T. And this is nothing like a square root of T diffusion process, which probably tells you that the permeability structure is very heterogeneous and or time dependent. But nonetheless, we can attempt to still bound what the values are to an order of magnitude. And so because this expands at a rate of about 5 meters per day, we can infer something like 10 to the minus 18 meters squared or so for a value of permeability within this fault zone. And so this is very low, but it's still going to be higher than the intact rock, the host rock surrounding this, because we don't see this flowing into that in terms of the seismicity at any point in time. So it stays within that fault zone surface that's tens of meters wide. Of course, as I said before, we don't really think that this is the best model for this. So I'm going to keep this at a very crude level. And so the final thing I'm going to look at here is in terms of earthquake source properties. And so here, I'm just going to try to speed this up a little bit because I'm running a little bit behind, but we're using a technique that comes out of UCSD over the last few decades that basically uses an iterative spectral stacking procedure to separate source and path and site effects. And so you're able to estimate source spectra from large populations of events. And then you can fit your source model to these spectra and estimate stress drops of each event. And so I'm going to walk through just very quickly the results of what happens with this. And so the first thing is looking at just the time dependence of the stress drops. And so here we're looking at the median stress drop over time within sliding windows of 500 events. And so we can see that the median stress drop goes from about 5 to 8 MPa, and it's kind of oscillating like this up until the second that the magnitude 4.4 happens, when we see this pronounced drop down to a median of about 2 MPa and stays low for about 90 days. And then we see this recovery of the median stress drop to values that are basically pre-event values. And so we can try to get a better sense of what's causing this by partitioning this up spatially. And so here, this is all the seismicity before this 4.4, the largest event, and then this is all the seismicity after. And so we can see that pretty much all of the events below this inferred barrier point that I talked about have colors that are yellow, blue, maybe green. And so that's on the order of 10 megapascals or so. Whereas all or most of the events after the magnitude 4.4 are much lower. So they're red and yellowish. But if you look carefully, this seems to be spatially segmented. So this stuff here above this barrier is also starting to be red and yellow, and that's even before this magnitude 4.4 happens. Whereas after, if you look below this barrier, most of these are still blue and yellow, which is similar to what it was before. And so these are actually spatially segmented. So we don't think that this is a change that's induced by this main shock. We think it's actually related to structural variability in the fault zone. And because this coincides with this inferred barrier to migration of the seismicity here at 6 kilometers, again, we think this is probably some kind of structural change, maybe some kind of lithological change or whatever, but this all seems to be happening at this, this depth range. So to kind of summarize the observations, we think it's something like this, where if you have a fault zone, something that looks on the order of this, it's not planar, it's got considerable curvature along strike with dip direction reversals. So there's kind of warping behavior. And within it, we see these kind of channel-like structures in the seismicity. And that might be something like this that you see here. And we think that this fault zone is connected to a deeper reservoir fluid that is initially sealed off. And somehow this seal breaks and allows for this overpressured fluid to be injected into this fault zone and diffusing through it. And so as it's diffusing, it's triggering earthquakes. And again, it's moving through this fairly narrow surface that's on the order of 50 meters or so wide. And so this model, this model has been called fault valving, and this goes back to the early 1980s from Simpson and Cox and others have done a lot of work on this. And although this original model was talked about in the context of basically having a big earthquake that would rupture down and break the seal, and then you would start having overpressured fluids injected. Here, we don't have a big earthquake to start this, so somehow maybe the seal breaks from some other means. But it's very similar to this type of behavior, except here we're seeing this observationally. So we think that this provides fairly good constraints on the fault valve model as a viable mechanism for seismogenesis in swarms. And so the very last thing I'll just mention is that you might be thinking, well, this is just one swarm. Does this really generalize to other places? How relevant is this? And it turns out that we've been looking at this now ever since we've studied this single sequence. We've been looking at this on a broader scale across the Southern California region. And here, this is kind of a bit of a teaser, but we've been able to see the same exact behavior in nearly 100 other swarms that are each at least 6 months to, in many cases, several years long in duration, all across the broader Southern California region here. And so this seems to be an important mechanism for fluid transport in the crust, where you have this type of episodic fluid injection process that's happening and driving all these earthquake swarms. So that's kind of more to discuss at another time. So to summarize, we've imaged this active fault zone hosting a 4-year-long earthquake swarm in Southern California, which is one of the longest that we've ever seen. The geometry of this is steeply dipping, but it's got significant curvature along strike. And within the fault zone, we see a lot of channeling that's mainly strike parallel, but sometimes it's a bit more vertically oriented. And the source of this swarm seems to be some kind of natural fluid injection process into the fault zone from a deeper reservoir. And the data suggests that this injection was sustained for around 3 years or more. And we're able to estimate the permeability of this fault zone to be something like 10 to the minus 17 to 10 to the minus 18 meters squared. And we infer that there's some kind of anisotropy to this permeability that's aligned with these channels within the fault zone. And we also see lots of barriers to flow or barriers to migration of the seismicity that might be geometric in origin. It might be lithological in origin. We don't really know what those are. And finally, we see evidence that the stress drop values are spatially segmented, which coincides with this permeability barrier that we infer. And this also points to some kind of structural control on the properties of this. And together, I think all of this stuff gives us a picture of how these kind of very heterogeneous properties of a fault zone can help to explain all of the complexity that we see within these earthquake swarms. And so I'll stop there, and I'm happy to take any questions that you have.
Super. Thank you very much, Zach. That was a great talk. The Q&A is now open. If anybody has any questions, please add them to the growing list we've already got in there, and we'll try and work through as many as we have time for and Zach has patience for. So to start us off, we have a question from Max Werner. What is the evidence that this swarm isn't driven by aseismic slip and not fluids?
Okay, that's a great question. So there's several lines of evidence for this. One is that the migration rates for this sequence are on the order of 5 meters per day or less, which is several orders of magnitude lower than anything that's been observed geodetically for slow slip events. On top of that, we see this radial diffusion pattern away from a point, which we expect for a diffusion-like process, although it's not a clean diffusion process. Another line of evidence is that the seismicity, if I can go back here, I'll just use this one here. Oops. The seismicity basically fills most of this surface here. And so if this was creeping, well, this is very different from, what you see at Parkfield, where it's mostly creeping with a handful of tiny asperities of stuck patches mixed in. You'd basically have to be going from creeping to locked in order to produce the seismicity at very short length scales on the order of tens of meters, which would be extremely chaotic. It's not like, we see on the Imperial Fault, for example, where there's planar seismicity at around 9 kilometers depth, and we think that it's creeping beneath that and driving this planar seismicity above it. Here, the fact that this diffuses away from this point and fills most of this fault surface with seismicity probably implies that that would not be a very favorable scenario. So we think all of these lines of evidence together suggest that this is fluid driven and not aseismic slip driven. But that doesn't rule out that there's not any aseismic here. I mean, we can't say that for sure, but we think it's primarily driven by fluids.
Super. Next question comes from Tom Winder. Where was the seismicity front located in comparison to the hypercenter of the magnitude 4.4 event at the time when that 4.4 occurred?
That's a great question. So it is right here. So the 4.4 happens right where my cursor is. So it was moving right up to it.
Super. Another question coming from this time from Jess Hawthorne. Do you see simpler square root of time diffusion on smaller scales within the average migration of earthquakes?
Maybe. If I go to this here, you can kind of see that this seems to start out very slowly. Then you can kind of see right here, at least, there's kind of like sub event nature within this. So this is kind of like a square root of t, but then it seems to start to do this again. So it's really hard to say at the aggregate of this. But I think that, just overall what we're seeing is very heterogeneous properties and potentially time dependence here. If it might be sealing up at some places, that can probably affect things. So, it's not just straight up injection continuously into, a bunch of fractures and just flowing through that.
And a slightly related question, if you look at an individual burst event within the larger scale swarm, do you see a decay structure that's more similar to a simple aftershock type sequence?
That's another good question. We don't really see that until the closest thing you would see to that is starting around this point, so several years in. And so you can see really from the first several years, there's really little to no clustering of seismicity that's present. You get occasional, very weak clustering. There's some striping here, for example, but it's very different from this stuff here, where you can just see this kind of pervasive striping over, several kilometers scale. So this is kind of the closest that we get to significant earthquake clustering within this sequence.
Okay, changing sort of focus of the question slightly. The inferred permeability value that you get, is that consistent with sort of other estimates for fault damaged rock?
Yes, it is. I would say. I mean, there's ranges for all this. This is going to be at the lower end of that range, but the rocks here are crystalline. And so, this is an immature fault zone. It's probably not so well developed. So, I would expect that this to be on the lower end for a place like this.
One from Richard Katz. What mass of fluid might have moved into this region, if your model is correct, and where might it have come from? And then there's a related question as well about the nature of that injected fluid and its potential composition.
Okay, so if you talk to the kind of numerical modeling community, the mass of fluid, the volume of fluid could be tiny. It doesn't take much at all. So it's very possible that this is not going to be something that would be detectable geodetically. And in our case, there was no geodetic evidence that was found for anything like that. There are studies that have looked at this, especially by Cox, looking at kind of fault zone hosted mineral deposits and trying to estimate the volume of fluid flux needed to produce those, and those seem to be produced episodically from other swarms that are believed to be fluid injection related. Those numbers seem to be consistent with what you would need from geological data. What was the second part of that question?
It was about what sort of potential composition or origin that fluid might have.
That's a great question. I mean, we don't really know. It could, I mean, it would just be speculation, quite honestly. We just don't know. This is not an area that people thought had fluids in it in the first place. So, and like I said before, we've actually seen evidence for this over a very wide range now. We just didn't even know that it was occurring here. So I think just this whole area is going to need to be reevaluated in terms of what we actually think about it.
Question from Tom Hudson. What do you think causes the shadow or the lack of seismicity after that magnitude 4.4 at the gap in the barrier that you have?
The shadow at the gap.
I guess.
This here is probably what he's talking about. If I had to bet on this would be the rupture area for that 4.4 or a big portion of it. And so this would be, the area with the largest stress change. And so therefore you can't trigger too many aftershocks within it. And that's been observed for many events over the years where there's kind of this anti-correlation of seismicity, of aftershocks and slip models.
I guess on a related sort of topic, question from Tim Greenfield about the aseismic regions. Do you think these are regions with very low permeability, with no fluid, or regions which for some reason just don't host earthquakes, or when earthquakes aren't induced?
That's a great question. So I'll start this out by saying that we can't tell from the seismicity because that's our only observable. However, in a young fault zone like this, I think it's probably reasonable to expect that this fault might be, a single structure that's kind of embedded within a more intact surrounding medium. Maybe it's got distributed cracking and things like that, but it might not be a localized interface that's capable of producing earthquakes everywhere, right? So, this is a fairly small fault. It's only a few kilometers in the dip direction. So it may very well be that you're geometrically constrained by where the fault zone is localized. But it could also be diffusing outwards, and maybe there are other faults that just aren't at the right conditions to see that. So I will say that you can't see it from any of these plots, but there are a couple clusters that are several kilometers kind of east of here, which were activated as well, but it's not clear exactly what the relation is with this one.
We're rapidly approaching 4 o'clock, but we'll just finish up with one last question on sort of context. So Andrew is asking whether you see the same patterns in artificial injection systems.
Yeah, that's a great question. It's so far, this seems to be many aspects of this are different, but others are, I guess, the same. If you compare it to something like Oklahoma in the US, where there's tons of wastewater injection going on, the behavior of this seems quite different, in part because I think the diffusion rates are so much lower. So there, the permeability is just it's just a totally different thing, and so it's just kind of flowing all over the place and entering faults that are everywhere and that kind of thing. Here, this seems to be kind of right into this single structure, and the source is very close by. So that one of the things that's special about this is that everything is kind of happening in slow motion, and we can really tell. We can make very precise measurements. With a lot of the other induced seismicity experiments, things are so quick that you can't necessarily separate the different effects there. So that's one of the things that we're fortunate with for this data set, that we can attempt to decompose this into the different components.
Super. Apologies to the few remaining questions. We're sort of out of time. So all that remains is to thank Zach once again for an excellent talk. Thank you all for joining us today. And don't forget to join us in 2 weeks' time for the next Earth2Earth seminar, when we will have Natalia Gomez and Jerry Mitrovica talking about ice sheets and sea level change in a changing climate. Super. Thank you once again, Zach. Thanks very much.
Thank you.